We're getting close to doing some math. But before we get to the math, we have to figure out where the numbers come from. So today I want to talk about measurement. Because with measurement, what we're doing is we're quantifying something that we observe. And we can actually make choices in how we quantify this information. So what I want to do today is just very simply and softly go over how it is that you, as a researcher, can make a decision to quantify something and what options you have available to you. So let's start. In the statistics lingo, we often talk about variables. And a variable is anything, any number, any observation, any data that is allowed to take on different values. It varies. It's a variable. Somebody tell me the opposite of a variable. A what? Yeah. The opposite of a variable is a constant. Give me an example of a constant, somebody. It's a number that cannot take on a different value. It could just be a number. We have a couple of famous constants that everybody should know, regardless of whether or not you're good at math. Pi. Right? Why is pi so famous? Pi is never ending. There's no last final digit. Right? It goes on and on and on and on forever. The decimals never repeat. So pi is sort of famous for that. When I was at Michigan State, they broke the world record for the number of digits of pi. Like, this is a supercomputing question. They went like billions of digits down. Okay. No, just something that they do. Not a math camp story, just something that they do. That there are mathematicians constantly working on this pi thing. See what's there. Why not? Why do we climb mountains? Because they're there. Why are we trying to find the end of pi? Because it's there. Maybe. Maybe not. Okay. Another one, if you've ever seen this equation, E equals mc squared from Einstein, energy equals mass times a constant squared. Well, what is that constant? It's the speed of light. We think light only travels in one speed. It's a constant speed. So we can plug that c into the equations. There actually is a number. Let's just go with really, really fast. Okay. So we have variables and we have constants. We're going to come back to the constant at the end of the class when we do ordinary least squares regression. But we'll just for now, let's think about variables and constants. When we make a decision to make a variable and how we measure a concept, we have a choice to make. Measurement is a choice. An old professor of mine said, we don't have measurement, we have measurement theory. And when you decide to measure and quantify something, you have to explain the theory behind why you measured it the way you did. If I'm to say which is the best way, with best in air quotes, I would say that a continuous variable is the air quote best way to measure. In a continuous variable, we assume that we have an infinite range of numbers. So if we draw a number line, what are our two endpoints in an infinite range of numbers? Yeah, we can go to infinity or backwards to negative infinity. Okay. So a continuous variable has no limit. Not only does it not have a limit in terms of the endpoint, but let's think of a number like pi. There's also no limit to the precision of a number of a continuous variable. Not drawn to scale. If we put pi here, what is pi? It's 3.14159, and then I could just do a whole string of numbers and you would agree with me. Because that's about as far as anybody ever remembers what pi is. But when we use decimals, there's also an infinite, I guess, range or length. Let's go with length. There's an infinite length of any number. So the next time you get a little goofy and stare into a candle for a while, think about, are numbers real? Because numbers are never what they say they are. They're always an approximation. They're like, we gave up. We're not going to measure any more decimal points. And that's why pi is 3.14 for some people and 3.14159. Maybe. I don't know. I could be wrong, right? So numbers are never actually real in a continuous situation. A lot of times we're limited by the tools that we use to measure. So somebody give me an example of a continuous variable that we talk about in our daily lives. A number that has lots of range. We're very keen on knowing what that number is going to be every day. The temperature, okay? So the temperature itself can have quite a range to it. Can it go from negative infinity to positive infinity? No, we don't think. We think that there is an end point, right? What's the end point? What's the coldest it can get? Right? There's this thing called absolute zero. The problem with absolute zero is we can't observe it. Because there can't be something colder than absolute zero to make the thing that's almost absolute zero cold enough to be absolute zero. So there's nothing to draw the heat away from the thing that's this close to absolute zero. So it's a theory. We're pretty close. And under absolute zero, we believe, theoretically, that all motion in an object would stop. So the little tiny atoms that are moving wouldn't move anymore. It's the absence of energy in an object. That's how cold it would get. But when we do temperature and we talk about that, we use different values for temperature. So the temperature outside, we'll usually round it to a number. Actually, usually tens of numbers, right? How hot is it going to be today? It's going to be in the 90s. If we want to get really specific, we'll say it's going to be 95 degrees today. But that itself is an approximation, because there's a difference between 90, 95, and 95.1, and 95.2. And when you take your temperature, What should our resting temperature be? 98.6 degrees. All right. So the tools that we use tells us when it's close enough. When we do money, how do we usually talk about money as a measurement? To the hundredth, right? $4.99. Except there's one place in public where we go to the thousandth digit. Gas stations. What the hell is up with that? It's a marketing scam, right? So the gas is $1.87.9. Well, that's different than $1.88. We do the same thing with exchange rates. We do the same thing with interest. We typically round it up to the next hundredth, which we call in our money a cent. Okay? So we have cents. Even though out there in the world are the really, really tiny fractions. Somebody's having a flashback to Office Space. Where they're not really stealing the money, they're stealing the leftover fractions of the pennies, and they're adding them up over time. That's your second homework. Go watch Office Space. Okay. So this is the air quotes best way of measurement because it is the most precise. It allows down to the very, very, very small decimal. So we typically think of continuous variables as the best. When we can't measure a concept in terms of a large range of values like that, we've created a form of measurement known as discrete variables. Now, with a discrete variable, there's no decimals. So the number is what the number is. There's nothing infinitely into it. Between any two values is nothing. So the number of children is a good example. How many children do I have? 2. Not 2.3. Not 2.8, not 1.75, because John's got that brain thing and he's not all there all the time. He's fine, he's 3. All right? They are whole numbers. It is an exact measurement. I can go home and look at my kids and go, 1, 2. Right? No need to light a candle and think about this one. This is sort of the fingers and toes version of measurement. But how I do that, I still have options. Okay. What the number means matters. Now, this sort of measurement, the number of children, that's known as a count variable. How many states do we have? How do you know we have 50 states? You can count them. How many individuals were killed by the police last week? I don't know, but we could count them. That's exactly what we call them, a count variable. All you need to do is count the number of times an event happens, and that's a count. It's discrete because there's no half bodies. Right? I don't have half a child. We don't have half of a state. It's still an exact measurement. Famous example in statistics, somebody wanted to study, and I'm not making this up, the number of horse kick deaths during the Napoleonic Wars. So what is a horse kick death? When a horse kicks a soldier and he dies, that's a horse kick death. And it turns out the more horses you have in your armies, the more horse kick deaths you have. A statistics company, Stata, actually uses that as its logo. There's like a little soldier, and then there's a horse kicking it in the head. It's better than that because I can't draw, but all right. Horse kick deaths. All right. That's a count variable. We can make it a little bit more complicated by recognizing that sometimes we're not counting when we assign a number, but we're classifying. Or we're discriminating. That word discriminating, before it became a bad word, was actually a math term. And to discriminate just means to classify or categorize. So imagine if I needed to take you all and separate you into bins. Like you can picture really big recycling bins. What are some of the ways in which I could do that? Not including the one on the slide. Why wouldn't I do age? It's not visible. It's also not nominal. What is age? Age is a number, yes. How do we measure age typically? In years. And how do we do that? We count them. So age is a count variable. And it can sort of be continuous depending upon how specific we want to get in terms of the number of seconds you've been alive on the earth. Then it can be a really big number. You're getting older every second. Right. How else can I categorize you? Okay, I can use gender. That's a bin. What other bins can I use? Hair color or eye color? Let's do that one first. I like that one. I have blue eyes. Raise your hand if you have blue eyes. Actually, raise two hands because you're that awesome. All right. So the four of us blue-eyed people, we go here. Everybody else, you go over there. Wait, are there other eye colors? You think so? What are the other eye colors? Brown. All right. Green. Any others? Hazel. Okay. So we'll take everybody and we'll categorize you. If I just put you into different bins, like with a religion, Catholic, Jewish, Muslim, Buddhist, Shinto, Scientologists, Mormons, apparently devil worship is on the rise in the United States. I've also learned of a guy known as the Flying Spaghetti Monster. All right. We could go down on through the list. Right? And we can just put you into bins. Now you'll notice I have a number here, right? With a nominal form of data, the number does not matter at all. It only serves as a placeholder for the bin. I could put any number up here. I could make this 600. I can make this 15, 43, 111, 3, and 21. The numbers do not matter. The only thing that matters is that there's a grouping that corresponds to that individual number. When you think of nominal, think of named. Okay? A nominal variable is a named variable. We can name the reason for your classification. Because Shinto is the name of a religion. All right. But what if, once I've classified you, I think that there is some order, that there is some preference? And back to my eye color example. We have blue, we have green, we have brown, we have whatever that other thing is. Which one's the best eye color? Jake, what's the best eye color? Blue. Why is blue the best? Because it's pretty. Aaron, do you agree? See? Aaron agrees, Jake agrees, I agree. Blue is the best eye color. Well, if blue is the best eye color, what's the second best eye color? Green. Why? Because it's the closest to blue. It's just got a little yellow in it. Right? Green is clearly second best. I mean, the people with green eyes wish they had blue eyes, but they're happy that at least they're not the people with brown eyes. Because nobody wants that. That's not pretty. What? It wasn't. I didn't say you weren't pretty. I said your eyes weren't pretty. Or your eyes aren't as pretty as they could be if they looked like mine. All right. That has an order to it. There's a preference. We are saying that blue eyes are better than green eyes, and green eyes are better than brown eyes. And if you want me to make you brown-eyed people feel better, well, brown eyes are definitely better than having no eyes. We can all agree on that, right? Okay. If we establish an order, either in one of two ways. One is a preference order. I don't know if you can tell, but if you're going to create data and you're going to do it this way, you better be really careful. Because what have I imposed upon this order? Yeah, my opinion, my prejudice, right? Why are blue eyes better than all the other color eyes? Because I have dreamy blue eyes. All right? I have taken my individual bias towards blue eyes and imposed that upon the data. Eye color should be what form of measurement? It should be nominal. But if I, as a researcher, choose to make the argument that blue eyes are better than all the other eyes, I can make that choice. I can take my bias and my prejudice and roll it in there. Just be careful, because there might be that one person who's like, nope, your list is wrong. Actually, green eyes are better because they're rarer. Right? We only have one green-eyed guy in here. Shh. Okay? Or you could say brown eyes are the best because most people have brown eyes. Okay. That's one way you could do an order. This is probably the better way to do an order. When the ranking is apparent to the people who you are measuring or who you're asking the question. This is known as a Likert scale. In a Likert scale, you're giving the respondent a range of values in which to place themselves. So for this ordinal data, there is clearly an order established. You could come up with a question and ask the respondent to give you their amount of disagreement or agreement to that statement. I would be happy if Hillary Rodham Clinton became president. Do you strongly disagree, disagree, neutral, don't care, don't know, whatever, agree or strongly agree? Okay. These are different categories. But what is the underlying value? What is it that we're actually measuring? How an individual feels about a Hillary Clinton presidency. Either in terms of happiness or displeasure. Right? That's the underlying trait that you're trying to measure. And it makes sense that the strongly agree is in front of the disagree, which is in front of the neutral, which is in front of the agree, and then coming in last is strongly agree. Now somebody's here going, well, wait a minute, didn't you order those wrong? Yeah, they can be in any order. The direction of it doesn't matter as much as the sequencing of it. And this is one of those annoying things. It could be 1, 2, 3, 4, 5. Just as easily as it could be 5, 4, 3, 2, 1. All that matters is that they're in sequence when you do that measuring. The other part about a Likert scale is typically we like the scale to be symmetrical. So if you imagine a dividing line across the middle and you were to fold it in half, that it should match up. So that's ordinal data. The last type I want to talk about is when you can't really create an ordinal scale, and it's a very simplified count. Fancy college word is dichotomous. A dichotomous variable. But that's a big word. So it's commonly referred to as a dummy variable. A light switch is a good example of a dummy variable. Off, on. Off, on. What trait are we measuring? I'll keep doing it until somebody tells me the answer. Whether or not there is? No. Whether or not there's light. Okay? So a light switch, just made it ordinal. A light switch The presence of a trait or characteristic. So if we're measuring light, 1 for on. Zero for off. Dummy variables are 1, 0. They're also known as binary variables. Light on, 1, dark, absence of light, 0, off. So if we were to measure male, do I get a 1 or a 0? I get a 1. Why do I get a 1? Because I'm a man. Okay. If I'm measuring female, do I get a 1 or a 0? Shut up, Nick.
0.
I get a 0. Why? Not a female. Absence of the trait. Okay. So gender, light switches. What else can you think of as a dummy variable? Hot or cold? That's a bad one. Why? Why is hot or cold a bad dummy variable? Okay, it's subjective. Why is it a bad way to measure? Okay, we have disagreement over hotness. At what point does hot become cold? Right? So there's a cut point, which is my last thing we'll get to in a minute. What's the best way to measure hotness and coldness? With a number, temperature, right? Unless you're asking somebody, do you feel hot or cold? But then, wouldn't you want to give them more options? Because there's hot, and then there's, I'm a little warm. And then there's comfortable, and then there's cool, and then there's freezing cold, get me a blanket. All right. So that's more of an ordinal scale. Give me another thing that is a dummy variable. Are you a child or an adult? What am I? An adult. Where's the cut point? Okay. So we could use something, we could start with something like age, which is continuous. We could also do an ordinal variable with age. We could do ranges. Okay, so we could do 0, let's say 0 to 3, 4 to like 11, 12 to 15, right? We could, if we're doing childhood development, right, we could say that there are different categories. And we could create a whole bunch of categories. And as long as they're in an order, then they'd be ordinal categories. All the way up to like senior citizen, and then there's the, oh my God, you're still alive. Do you want me to put a pillow over your face to end your suffering? That was an act of kindness. Don't be shocked. Okay. Or we can do, if we put in a cut point, we could say 0 to 18, or actually it'd be 0 to 17.99999, and then 18 to death. Why does that make sense? That an adult, you are an adult the moment you turn 18. Because that's what the law says, right? The Uniform Code of Contracts says that minors under the age of 18 cannot enter into valid contracts. We can use that as the reason for our cut point. But that's not really the cut point though, right? Because don't we have different age limitations for other things? 21 to consume alcohol. 25 to rent a car or a hotel room. Any others? 21 to have a concealed weapons permit. Running for office. All right, we have some constitutional barriers there, 25, 30, and 35. Okay. So we're going to have to be clear when we create our cut points, why we're creating them at that point. Anybody want to argue with me that gender is not binary? Anybody? You're being lazy. It's not. Gender is not binary. Right? Gender, you can have an ordinal or even just a nominal outcome to gender. And even the conventional male is a 1 because you have a penis and female is 0 because you have a vagina doesn't work. Anybody watch the Olympics? And there was that runner from some African country, South Africa, and she has a ridiculously high level of testosterone. Therefore, her body is a manly body. It has muscles where the men have muscles. Okay? And a bunch of runners are like, this is so not fair. Because if I were to take my testosterone levels up to hers, then I would run a lot faster. And so there are runners out there who think that she should have to take drugs that would suppress her naturally produced testosterone so that it would level the so-called playing field for runners. And that has nothing to do with the transgender movement. It has nothing to do with gender identity. It just simply has to do with whether or not an appendage gives you a trait or not. What do you do with XXYs? Or 2XY, whatever. There is a chromosomal defect out there where you have both genders. So you would have a third category. And the question is, do you make it nominal or do you make it ordinal? You stick them in the middle. Yeah. These are all theories. These are all decisions that researchers are making. And I'm out of time, so I must be out of ways to measure.